which is the starting point of our high-dimensional workshop. And this workshop I mostly use an excuse to invite people to input whom I either knew before very well or that I wanted to meet. And so Alex falls in the first category. I'm honored to have him as a friend from a long time ago. And he's also a pretty distinguished researcher in mathematical statistics and the intersection of that with optimization. So he'll be talking this week about high-dimensional statistics. I mean, this is intended as a course, so please feel free to ask questions if you have them. And without further ado, let Alex do the talking.
Thank you, Roberto, for the invitation. Really a pleasure to be here. So my intention here is to give this broad overview. This has been a field that has been growing a lot. There are many, many details and slightly different ways to approach the problem. I'm going to focus on one way which seems suitable for some class of problems, in particular some class of problems that arise in econometric applications. And we're going to discuss a few things, but I'm really going to start from the basics, assuming that people know only, not really know the high dimension estimation, doesn't really know some of the specifics. So today, I would like to start with some basic setting, literally mentioning least squares when the dimension that we have is smaller than the sample size, and then start discussing Lasso when the dimension is bigger than the sample size, and then start talking about penalty choice, probably in the next class, and conditions on design conditions. And then I'm going to start talking about variance of Lasso. I will switch for the next one. I will definitely switch. Then variance of Lasso. And then talk about post-model selection estimation. So all of that will be concerned with rates of convergence. And then I'll talk about building confidence intervals in this high-dimensional setting, which has some special subtleties that need to be taken care of. That's probably will be lecture 4. And then and everything is going to be done in the context of linear models. In the last class, I hope to have one full day to talk about the generalization of the results for nonlinear models. I'm probably going to mention examples of nonlinear models either today or tomorrow, but this is what I have been thinking. So this should be lecture 5, this should be lecture 4, this should be lecture 3, this should be lecture 2, essentially, and 1. It's going to be a little bit fluid, depending on how fast we can go, but that's kind of the brief sketch of how I intend to go. And I switch for the white chalk now. So what's the context, right? So it's really statistical estimation. And I want you guys to think about the simplest model people have been studying. Essentially, we observe an outcome y, and we observe covariates x. X lies in some potentially high dimensional space, Rp, and y is a scalar. That's kind of the context. You should think about we have observations yi, xi, which are IID for now. We worry about some generalizations later. And I want you guys to think about the linear model that y is generated as a linear combination of the axis plus some noise. And the basic assumption is that given x, the expected value of the noise will be 0, right? And we can also assume, we'll assume that the second moment will be constant, so it's going to be a homoscedastic model for now. We're going to assume further things when we go in a minute, but this is what I want you guys to think about. So the whole point here is that I want to recover the impact of the regressors on the conditional mean. So we're going to have the interpretation that the expected value of y given x is just x beta naught, and we want to recover this function, this function. So in the classic setting in which the dimension is either fixed with the sample size or is much smaller the sample size, it's well known for many, many decades, if not centuries, the best thing to do in this setting. We know that the vector we are interested on is actually the solution under mild conditions, is the unique solution of the least squares problem. And if you have data from yi, xi, for I equals 1 to n, a natural estimator for that would be just minimize the sample counterpart of that. And here, let me write also the matrix notation that I would use. So this is always going to be the same as what capital Y is collecting all the y's together as a vector, and x beta, x is just collecting each row of capital X is going to be the vector xi. And then just quickly go over why this is a good estimator. Basically, a simple proof for the rate of convergence. We know by the way, I also, for now, let me assume that the xi's are fixed. So I'm gonna worry about this fixed design, and then to understand if we have good properties, we're gonna have to essentially make some assumptions and show that these assumptions translate with high probability on good properties on the fixed design matrix that we are interested in. So to analyze this problem, I just want to highlight in this setting the two main issues that arise in this analysis. We know that by the optimality of the estimator, it fits the data better than the true value. So this is essentially a vector of all the noises. So this will be just and this, if I rewrite each one of those as y minus x plus x beta naught, I can just rewrite the sum as beta hat minus beta naught over n plus x beta hat minus beta naught to n. This goes away. And then we have essentially the two main issues that arise in these type of problems. So if I want to have a good properties in the estimation here, two things I'm going to have to deal with now. This part is essentially the noise associated with the problem. If the noise was 0, this would be 0, and then I would actually have found probably a very good beta hat that fits very well the data. But if I care about how these behave, I also have to have assumptions on the matrix X. If the matrix X is 0, then I'm going to have many choices for the estimator, so it's not really interesting. So there is these two fundamental issues. One is essentially the noise, a measure of the noise of the problem, and the other one is that my matrix X needs to be somewhat well-behaved so I can tell apart other vectors from beta naught. And that's what they call identification conditions. So one is to allow us to handle the noise. The other one is nice properties of the X matrix that we can actually allow us to recover. And so let me try to, in this case, make one analysis. And this is still in the case that P is less than N. So many things will make sense in this case. But when we're going to deal with the high-dimensional case, we need to understand the difference. We need to understand what needs to be relaxed, what needs to be fixed. So this problem, one way is simply to bound the noise by, we can do Cauchy-Schwarz here. And now to bound this part. So I'm going to do everything for fixed design, but once you have these assumptions, the calculations are essentially the same. But to bound that part, I can compute the square of the random term, and that will be essentially equal to the trace of epsilon x epsilon. We can exchange. This is just going to be expectation of trace. I want to do, so here's this. I want to do x epsilon. Transpose, then I can just do this. So now this is just the covariance matrix of X transpose epsilon. So basically what we get here is going to be, since the variance is homoscedastic is sigma square, we just get sigma square trace of X transpose X, which one can further bound by sigma square, the maximum angle value of X times dimension P, since X transpose epsilon is actually a p-dimensional vector now. So this will take care, if we apply Chebyshev bound, we actually know that with probability 1 minus delta, this can be bounded by sigma square root of lambda x and B over, and then have delta there times not. That would take care of the of the noise part, and here lambda max. Yes. And now, here's where I'm going to use some assumption on identification, is that beta hat minus beta naught, this will be at least, and then one needs to get used with the way the scaling works, but this takes the vector, this p-dimensional vector to a n-dimensional vector. So, and this is, once you normalize by root n, this is what we call the prediction norm. So it's the mistake you make in the design matrix you're concerned. So that's actually going to be the metric I care the most for now, divided by lambda mean of x plus x over n square root. So I just, whatever impact I have in this elliptic norm cannot be smaller than the impact of the minimum angle value. So this is a valid bound. So using this equation, we get x beta hat minus beta naught squared over 2n less equal than sigma lambda max over n lambda mean times square root of p over n. And then we have this 1 over square root delta, which is to have the bound with probability 1 minus epsilon, times x beta hat minus beta naught. Now we can cancel 1 over root n and one denominator on top, so we get, take this to the other side. So essentially, the rate of convergence with some probability is going to become some constant that depends only on the probability. So we get a rate of convergence that depends on the design conditions and depends on the square root of the dimension over the sample size. And this is the standard result you should expect from least square. It's optimal in the sense that there will be models that will achieve this rate of convergence. But this makes the case that this works if P is smaller than n, and if you have well-behaved matrices. If this design matrix x transpose x over n has bad angle values in the sense that the conditional number is large, this becomes a loser bound, and then you have issues.
Maybe I'll just mention to the students that that's exactly the matrix that I called sigma hat n. Right? That you take the rows are the x's. So when you look at x transpose x, you get that.
That would be.
That, then you get the sigma hat.
So I call this sigma hat n?
I called it sigma hat n.
Okay.
I guess it's like a covariance.
Yes, yes. And then probably next, tomorrow, what I'm also going to talk about is when we place reasonable conditions on how the x's are sampled at random, using random matrix techniques, you can show with high probability this matrix will be well-behaved. Now, so this is for the case, so indeed if P is much smaller than n, or if P is fixed, this gives you good rate of convergence. Now, if I want to handle the K, but the problem is that if P is bigger than n, now we're going to have an issue. First, this P becomes bigger than n, so this no longer goes to 0. And second, if P is bigger than n, so first implies square root of P over n goes to infinity as n increases. And that comes from the way we handle the noise. That's the first observation. I want to make clear the connection. This requirement comes from the fact that we're using this bound. Because the L2 norm here pushes a square root of P into the bound. The other issue is that this condition also implies that lambda mean of x transpose x over n will become 0. So it's not full rank matrix. So this bound becomes essentially infinity. So these are the two issues one need to think about when trying to generalize these and obtain some results for this high-dimensional case. And that was the idea that, okay, so for many years people thought that this case could not be handled. Indeed, in this case, this implies that least squares overfits. And you actually get a perfect fit, so you not really obtain anything from the estimation that's meaningful. And then people start looking in the 70s on regularization. And then they start to develop information criteria to penalize for having a lot of variables. And then that's on archaic information criteria, for instance, and the Bayesian information criteria came along. So the idea is that, okay, so in general, I cannot do anything. This is actually going to be bound, a bad bound. But if for some reason I have many of these coefficients equals to 0, maybe I have some hope. And they started thinking about how about solving problem doing an estimator of the form that I have a fit, but then I also penalize for the number of non-zero components that I have in my model. Essentially, I'm trying to balance fit with complexity of the model, and there were many results established there. But they first analyzed the case that P was less than n. But these ideas percolate, and in the 90s, people start to think, okay, if I want to apply these type of ideas when P is bigger than n, then first I need to be concerned with computations. And this estimator turns out has potential combinatorial search. There are some negative results in the worst case that these would be tough to do in some situations. And then in the 90s, essentially, a method that tries to achieve similar properties than that one, but with good computational properties was proposed. And it's called Lasso. And the idea is that instead of using this L0 norm to achieve a simple model, the idea is to use L1 norm, because that is convex, and then things can still be computed efficiently. There was quite a few results in the mid-'80s and early '90s showing that this type of problems can be computed efficiently in theory, and then many good methods came up in the early 2000s to solve those efficiently in practice. But for this to make sense, we need to think about our model. We can think about the same setting we had before. But with one extra assumption, that the vector that we're interested, the number of non-zero components equals to S, and that's much smaller than n. But here, the dimension of the vector is P, it's allowed to be much bigger than n. So that's the setting we want to study. Yeah. So you're trying to think about, okay, so what if I relax, I make this much bigger, so this will not make sense, but now I have more structure. I only care a few coefficients. It turns out that this actually has nice connections with non-parametric estimation. Because in the end of the day, non-parametric estimation, you're estimating this infinite dimensional object. You could estimate as long as you have a small approximation error, because you essentially truncate the series that you're going to be dealing with. Similar ideas can be applied here. I also like to work, especially when I'm dealing with econometric applications, that my model is approximately sparse, which means that I have an additional term here, which is an approximation error. Most of the ideas go through. There is a lot of extra technical work just to deal with it. For now, I'm going to use an exactly sparse model. But in many applications, it makes a lot of sense to understand that this sparse vector provides you with a good approximation for this conditional expectation. And then really ties nicely with all the non-parametric literature. Yeah. So if we want to analyze this now, under this extra assumption, let me just introduce one notation. If I have a vector delta, and I'm going to denote T, the support of beta naught, which is contained in 1 through P. So this is a set with cardinality S, contains a non-zero component, the index associated with the non-zero components of beta naught. And if I write delta T, this is a vector that the ith component of it equals to 0 if the ith component, the j component, if j does not belong to T, and is delta j if j belongs to T. So it's just a truncation, essentially a truncation to the set T. That's kind of going to be useful in what's going to happen now. Yes. Now, so let me try to write some rate convergence for Lasso now. And the way we start is essentially the way you start all these problems. The only thing you know by definition of the estimator is that in the data, you fit the data better with the estimator than the true value. And then we can apply the same idea there. Here, this is just the error term. This is the error term plus x beta hat minus beta naught. And then we get 1 over 2n x beta hat minus beta naught square minus epsilon x beta hat minus beta naught over n plus lambda beta hat 1 is equal to lambda beta hat 1. So at that point, we're going to have to, if you try to proceed for the same type of analysis we did before, this is the noise term. We have the identification here, but we know this is rank deficient, so that's going to be an issue. So lambda mean here will be 0, so that would prevent our analysis. If you try to do Cauchy-Schwarz here, as a square root p would show up, and that will be too large for square root n to take care of it. So it's here one departure from the standard analysis. In the standard analysis, when p is small, L2 norm is controllable, it's manageable. But when we go for high dimensions, L infinity norm is a much nicer object to be controlled if the vector is huge. So one key aspect of this high dimensional literature is that you need to move away many times from the L2 norm to work with L infinity norm. And then if you are working with the infinity norm, the dual of it is going to show up to produce bounds. And that's why L1 norms are going to show up. And that's precisely the penalty here. So that's how these things actually work, and that's how these things merge together. But the noise of the problem, which was that was this term. The way we're going to control it, it is going to be through holder. And here is going to show up the L1 norm, so we can control it. So when you look at that term, that's what makes you going away from beta naught. Your regularization is lambda times the L1 norm. If you are in the case that beta 0 is 0, this will be just beta hat, will be precisely the regularization. So this piece is what you want the regularization to majorate. There will be some extra work to deal with the fact that you have the difference here, but that's precisely what this is doing. Essentially, the noise is being majorated by this. We're introducing bias towards 0 to kill the noise, and then good things potentially happen. And so to continue the analysis, I'm going to make one assumption, that we are in the event that lambda, the penalty, is bigger than some constant bigger than 1 times x transpose noise over n. So this is, let's say, the event E, and I'm going to assume this event occurs. So then it's going to be important to actually look at what are the good choices of lambda that make sure that we're going to set lambda such that probability of this event goes to 1 as n goes to infinity. Right. So I want to defer that for a moment, but that is going to be one thing that we're going to have to deal with. And then we're also going to have to deal with the design condition. But let me just, and here C is bigger than 1 is fixed. Think about, people typically in the literature propose 2 or 1.5, 1.1. It's not really relevant here, but so, and we still have this relationship here. So let me take this to the other side. We have x beta hat minus beta naught square 1 over 2n. Now, the noise term, I can minorate it because on the left-hand side by x epsilon infinity over n times beta hat minus beta naught 1 less equal than lambda beta naught 1 minus lambda beta hat 1. So this piece, this is positive. This needs to be greater or equal than 0. So, and this is at most lambda over c. So we have minus lambda over c, beta hat minus beta naught 1, less equal than. So here, let me split this L1 norm into two components. Essentially, this is equal to beta hat at the true support, the L1 norm on that, plus the beta hat outside the true support. So L1 norm is just the sum of the absolute value of the components. So I can split into the sum over the true support and the sum outside the true support. So I can take this piece and subtract this piece, and then I can further modulate that by beta hat t minus beta naught minus lambda beta hat t complement. Now this side, I can do the same split. So this side is beta hat t minus beta naught, norm 1, minus lambda over c, beta hat t complement beta naught. Now, let me just take this to the right-hand side, take this to the left-hand side. I get lambda 1 minus 1 over c, and remember c is bigger than 1, times the estimator outside the true support, the L1 norm of that, less equal than lambda 1 plus 1 over c. T minus. So this is the complement of the support. Right. Oh, sorry. That's definitely, yes. This is just a split between those two, yes.
Yeah, so you're just using the fact that the complement of the support beta hat 0 is 0.
No, this, yes, I'm using the fact that
Right.
this sum here minus beta naught 1 equals to the summation for components in the support beta hat j minus beta 0j plus summation outside the support the complement beta hat j, because indeed those guys are 0 outside the support. So lambda actually vanish here. And here actually means that the vector beta hat cannot be in any set. It needs to be in a set that the mistakes you make in the L1 norm outside the true support are essentially bounded by a constant times the mistake you make inside the true support. If the true support is small, it's kind of a small dimensional object, you have hope that this part is not really too big in terms of dimension, effective dimension. So the mistake in the high dimensional space is controlled by the mistakes you make in this small dimensional space. This is a Kohn condition, not this, but this could scale, but that makes us to define this set, which is a set of vectors delta in RP, such that the L1 norm of delta outside the true support is smaller than a constant C bar times delta in the true support.
So, yeah, again, I want to say something to the students. So we saw the same set last week, except it was called CS kappa. So he calls it. Yeah, maybe I should have asked what notation you used before I,
Okay.
before I define it. So my S is his T, and my kappa is his C bar.
C bar in this context is just going to be C plus 1 over C minus 1. That's where we need C bigger than 1.
Yeah, so that means I think I'm talking about the.
That's fine. That's fine.
Yeah, I
That's
just
fine.
want to make sure that they see the connection, right?
Oh, yes, yes,
So
yes.
last week we're discussing compressed sensing, this L1 digitization algorithm, and one of the things that we showed is that the difference between the beta hat vector, the vector we're going to found,
it's a little bit different, and there are ways to make this a little bit sharper. So this is one that makes the proof more or less short. And I'm going to discuss later some variants of Lasso, and one of the variants would be the Danzig selector, which would allow you to get the CS1 that he's mentioning. But now the hope is that, okay, in this set, now since I restricted this set, I don't need to look at any possible directions now. So if I look at the identification condition, instead of using the worst possible direction for my design matrix, I only need to look at directions that are in this set. So that's where people propose in the late 2000s one quantity, let's say kappa, associated with this constant, defined as the minimum over vectors in this set, in this restricted set of x delta 2 norm of that divided by root n. That's just a normalization. Divided by the L2 norm of delta in the true support. And this is called restricted angle value. And we're going to assume this is positive. And next class, I hope to show you that there are few sufficient conditions that are meaningful in different contexts for this is a good condition. But this for tomorrow. But I want now to finish the rate of convergence for Lasso using that. And to finish the proof, I'm going to start from this piece. From star, we have 1 over 2n x beta hat minus beta naught square less equal than, this is majorated by lambda over c times the L1 norm. So we get lambda over c plus, then here we have the same condition, lambda beta hat t minus beta naught 1 minus lambda beta hat t complement 1. So these are going to split into the two terms, one in the true support and one outside the true support. That gives me 1 plus 1 over c lambda beta hat t minus beta naught 1 plus lambda over c beta hat t complement minus lambda beta hat t complement. And this cancels out. Essentially, I can majorate that by 0. Now, this is only happening in the true support. So the maximum number of non-zero components here of this vector is S. So I can relate the L1 norm to the L2 norm without paying too much of a price. So lambda 1 plus 1 over c is square root s times beta hat t minus beta naught, the 2 norm. Now this part is where I'm going to use the restricted angle value. Because this would be my delta, t. So what that condition is telling me is that since this vector beta hat minus beta naught belongs to the restricted set, I know that x beta hat minus beta naught over root n is at least kappa c bar times beta hat t minus beta naught. And this is what we have here. So I'm going to further majorate this piece by this predicted norm divided by kappa. Now I have the same term on both sides, except here I have the square. So the prediction norm rate for the Lasso estimator, I'm going to take the 2 to the other side, is 2 times 1 plus 1 over c lambda square root s over kappa. Now, 2 things I haven't told you. How much is kappa that comes from this condition? And what was the choice of lambda that gives me that? So I can actually compare the rates. So the way you should think about rates for the least squares is just up to a constant. This is the rate. It depends on the probability. That's the rate of convergence. So here, and that's where I want to next class go into details on the choice of lambda, but if we think about a very standard case where the errors are normal, 0 sigma square, a choice of lambda that will work needs to, for this to happen, we need lambda bigger than this quantity. Now, if this is normal, if you normalize the columns of x, which is a typical assumption there, you essentially get this is the maximum of 1 over n summation of xij epsilon I. Now, a typical assumption that people use is that the columns are normalized so that this equals to 1. So each row actually is a normal with 0 mean and variance sigma square over n. So by a union bound, you are taking the maximum of those. So we want to find lambda that's bigger than the maximum over j of 1 over n summation xij epsilon I. This is so this is less equal than p times the maximum over j probability of lambda less than 1 over n summation xij epsilon I. Under that normalization, this essentially is a normal. So these can normal is 0 sigma, so this is p e minus lambda square over 2 sigma square. I might be missing a constant, might be missing a 2. I probably could cancel with the square root of 2 pi. I'm not too concerned there. So if you want this to be delta, if you want this to be smaller than delta, we just need to set lambda bigger than, and there is a n there. Square root of log p over delta over n. So, and something of this type. There will be a constant there. So that is a crude choice of lambda. That works. But to get rates, that's what I want to keep in mind. So lambda would work with square root of log p over n. So the rate so this would happen with high probability. So the event that we need to happen probability goes to 1. So basically, the rate we have is a constant times square root. We have s log p over n. We don't have kappa. Under reasonable conditions, kappa is going to be fixed, bound away from 0. So that's become a constant. But now, when you compare with the previous case, the gains in terms of the n, we cannot beat that. That's what is the rate you should expect, 1 over root n. But the dependence on the full dimensional, instead of p, goes for log p, and you pay a price by the sparsity there. So now the effective dimension becomes s log p. But this allows you to have a dimension p that's much bigger than n. And that's where it really pushed forward the literature in many applications. That all of a sudden you can run these tools as long as this piece goes to 0, so n needs to be bigger than s log p, you can get consistency. And that motivated a lot of interest on that. It really pushed a couple of things. So I want to leave a more careful analysis for the choice of lambda for next class, because there was a sequence of papers that actually improve on that choice. So I want to discuss that in more detail next class. Also talk about the conditions to show that this kappa is actually well behaved for next class. And I have 5 more minutes. I don't know if I should start something extra now. So it's just to motivate uses of that of this tool. So basically, we just saw this very simple model, right? This linear model. So we have x beta plus some noise. And so here we want to estimate the conditional mean. And where I came from in terms of motivating applications, this is used a lot to understand, for instance, how age of workers change with education, age, and a bunch of other factors. So these are the type of applications that in econometrics people will be concerned with. What's the expected wage per hour of an individual if it gets 1 extra year of education? So here y will be a continuous. We're also going to use these tools when we want to actually estimate y is actually binary, and the expectation of y given x is the logit function applied to this x beta, and the logit function of t is just exponent of t over 1 plus exponent of t. So for instance, it's estimating a probability, and typically we want to understand what's the probability a country is going to enter in recession given some economic measurements. That's very interesting. So it's very noisy, but there are tons of things you want to control for, how you find good estimates. So another type of applications we are concerned is that many times you don't care about the average behavior. So many times you care about some extreme event. So for instance, if you want to understand birth deaths, right? So basically what happens there, birth deaths are extremely correlated with birth weight. And then if you want to understand what drives a birth weight to be low, but on average, birth weights, they're fine. So you don't really care about the average behavior. So what happens there is that you care about the birth weight, but at a particular low quantile. So instead of estimating something that gives you the conditional mean, you're really defining this to be the tau quantile of y given x is x transpose beta tau. And you're interested on low quantiles, on quantile 0.05, 0.01, so that you understand which factors are actually important for that low quantile. The interesting thing about quantile estimation is that I might be interested at quantile 0.05, but I might also be interested at quantile 0.1, or for that matter, also at quantile 0.9. So what happens is that when you're doing this, we're actually interested on these coefficients beta tau for tau in some compact set U containing 0, 1. So what we're actually doing there is estimating functions. So here we're going to be estimating, and this is a p-dimensional vector for each tau. So estimating p functions, which domain are U. So how you, with a finite amount of data. We always, only thing we're going to have is yi, xi, I equals 1 through n. But you want to recover these whole functions of those. And we can put those, allow p to be much bigger than sample size. 4. So other applications we have is that if you go back to the very first one, but you no longer have that expected value of the error term given x equals to 0. So we have some endogeneity in the problem. So all of a sudden, I don't have the nice zero mean condition, but I still want to recover beta naught. So then here we're going to have to somehow use additional information. So for that's where instrumental variables kicks in. So one problem that I work on that is if you want to estimate the impact of the eminent domain practice of the government on the economy of, let's say, the prices of how they influence the prices of houses. There's actually an endogeneity problem in this setting because the practice of the government might be related with shocks in the economy. So those things are not exogenous. So the shocks of the error terms, they are correlated with the government's decisions. So if you try to estimate the coefficients, you're going to get bias. And you need to come up with some extra information to actually be able to correct that bias. But this extra information turns out to be very high dimension. So you want to do model selection on those variables as well. And more generally, you want to have a problem that's defined through M estimation. So basically, you define your beta hat, in this case of Lasso, to be the minimizer of some criteria function based on the data of beta plus the L1 norm. So many many problems will fit this framework. So, and I hope to touch in some of them later. Most of the time I'm gonna stick with the first one because proofs are cleaner, but I hope the last class will be, I'm gonna pick one of these to worry about. And I think now it was my time, so I stop now.